Generating the frequency response of any network in Matlab can actually be accomplished rather simply, granted that one has knowledge of that network's transfer function. Now here is a simple filter with common linear circuit elements, all of which we're aware of. So we're going to take this filter and we're just going to find the frequency response of it. Now, we already know the frequency response of it as it's already been run in PSpice. This is PSpice. And, well, it's been provided with values such that its frequency response tends to dip around 1 kHz because this is a band-stop filter. Now we are going to construct the frequency response of our circuit, but before we do that, we first need to define the transfer function describing said circuit. So we're going to do that by entering all the values for all of our circuit elements. So in this case, okay. Now our transfer function can just be found using TF, short for transfer function, and we're going to define our system as sys1, and that's going to be equal to TF. Now the input arguments of transfer function is really simple. It's just 2 arrays. The first array in your first argument is just going to be the coefficients of the numerator of your transfer function, and the second input argument is going to be the coefficients of the denominator in your transfer function, as you might have guessed. So we're going to write those as follows. So now we have actually defined our transfer function. In addition, we must specify the range of frequencies to be swept by Matlab. Now, because our circuit had a resonance frequency of about 1 kHz, the set of frequencies in question should be centered around 6,000 radians per second. So we're going to just identify that really quick, using log space, of course. We're going to have 50 points. Now our bode function is going to be actually really easy. All we're going to use is our transfer function as the input argument for the first one. The second one is simply going to be our set of frequencies. Now if we input that, we should get our bode plot. And there it is. So as you can see, it's centered around. Now if you click at the bottom, you should see, it should tell you the radians and then its corresponding degree. Likewise, you can do the same thing on the magnitude plot. You can actually click at different points and it will tell you, and actually keep it there too. So you can actually take a screenshot of this or put it in a Word file or something to show that you actually carried this out. So that's actually pretty handy. So as you can see here, it's around 6K radians per second. So that's the plot of your frequency response using the bode function. However, if you wanted to get really fancy, you can actually plot more than one frequency response at the same time using the bode function. But first, let's find another transfer function representing another network we would like to analyze. In this case, let's consider a bandpass filter. So now we're just going to simply define its transfer function, which luckily I've already mapped. So just to see we're consistent, transfer function, look at the numerator, 1 over RC, denominator, and everything sits to fit perfectly, so all is well. Now that we have defined that, all you have to use bode, have your systems and your arguments, and keep in mind that you can actually plot as many of these as you want, as long as they just follow one after the other, and just make sure that your last input argument is simply the frequency. Now if we plot it, notice that this graph is consistent with the properties of both filters, as signals that are passed through the bandpass filter at resonance frequency are negligibly attenuated, and those that are near the resonance frequency for band stop filter are heavily attenuated, concluding the operation of the bode diagram in Matlab. Well, there you go.